by Professor Zhang and Gabriel.
Okay.
Please.
Yeah, thanks for staying at this hour. This is joint work with Gabriel Kong. So let us start with the standard model of information geometry. The standard model, namely, we give a parametric family of probability distributions or statistical models. Here, P denotes that. So omega denotes the random variable in the sample space. And then X denotes the parameter. Okay? So given that parametric statistical model, we can construct a second-order invariant, Fisher-Rao metric, and a third-order invariant, the Amari chains of tensor, and by taking the derivatives of the log of the model with respect to the parameters, second-order pairwise correlation, and then the triple correlation. So Amari chains of cubic form is a symmetric 0, 3 tensor. And then we can construct the family of alpha connections by first taking the Levi-Civita connection of G and deform it with the Amari chains of tensor. And that gives rise to the very well-known alpha connections. So in this model, which is now the standard model of information geometry, which is also the so-called statistical manifold, the connections that's generated, the alpha connection that's generated are all torsion-free, and they are all coupled or quasi-coupled to the Fisher-Rao metric that's generated. So because of these two properties, the manifold endowed with the Fisher-Rao metric as well as this connection structure is called the statistical manifold. That's the standard model. So in this talk, we are going to present or propose an alternative model for the parametric family of probability density functions. So in this alternative model, we would like to model this parametric family as a partially flat manifold, and I'm going to explain partially flat. So partially flat manifold is a manifold which has a flat connection, but not dually flat. One of the dual connections is flat, but not dually flat. And in this model, the connections are both curvature-free. Both of the pair of connections, 1 and -1 connections, are curvature-free, but one of them may carry torsion. And furthermore, these pair of connections are not quasi-coupled with respect to G, which is still the Fisher-Rao metric, which in general case may not be a Hessian metric. Okay? So this alternative is essentially what is known as the statistical manifold admitting torsion, which was first studied, proposed, coined by Kurose, and officially appeared in publications by Matsuzue and Hemi. So for this model, we call it B model here, stands in contrast with the A model or the standard model in the following way. Well, let's see the case of the dually flat Hessian geometry. So in A model, according to the standard model, Hessian manifold arises when the pair of ±1 connections are curvature-free. In this model, in the B model, the Hessian geometry arises when one of these connections, when actually both of these connections are torsion-free. So in the B model, the connections are always curvature-free. The +1, -1 connection are always curvature-free, but one of them may carry torsion. So when both of them are torsion-free, they become the Hessian manifold. So this perspective changes from connections which admits curvature and torsion-free to a case of connections which are generally curvature-free but admit torsion. Okay, so this change from curvature viewpoint to the torsion viewpoint, and in some sense, it mirrors the alternative model of general relativity theories, where there is an Einstein-Gattang theory of gravity in physics, which is somewhat different from here, but that's the general spirit. So let me explain how this works out. So we are given with a real differentiable manifold and a semi-Riemannian metric on it, and let nabla denote an arbitrary connection which may admit torsion or curvature. we have the standard definition of the conjugate connection, the G conjugate connection, as the connection which jointly preserve the two vector fields x and y. X and y are vector fields, z is another vector field, and you have covariant derivative of nabla on these vector fields, and if nabla star and nabla jointly preserve these vector fields with respect to of G, then they are called conjugate, and it can be verified. This indeed defines nabla star is an affine connection. So with this definition of G conjugate of a connection, note here we have made no assumptions about curvature and torsion of these connections. They can be arbitrary. What is known is that the curvature of nabla and nabla star are related by a very simple formula, which essentially says one is the opposite of the other, which means that if one of them is curvature free, the other is also curvature free. So if one of them, if R of nabla is 0, then R of nabla star is also 0. Okay. Now, the relationship of the torsions of these two connections are somewhat complicated. So you can derive, one can easily derive, and this is also known, well known, that the difference of the torsion of nabla and nabla star equals the right-hand side of this complicated expression. And this right-hand side, when equals 0, it turns to be called quasi-coupling of nabla and G. So another way of saying is that when nabla and G are quasi-coupled, then the torsion of nabla and nabla star are the same. So from this, we can have the following definition. The first is a very familiar one. Nabla and G are said to be quasi-coupled if this equation is satisfied, which essentially would make the torsion of nabla and the torsion of nabla star equal. So that's a standard definition of quasi-coupling between nabla and G. Okay? So if you read one more, if on the right-hand side, if it's quasi-coupled, then the left-hand side is also 0, which means the torsion of the nabla and nabla star are 0. Now, we coin or propose another term called torsion coupling between nabla and G. So torsion coupling is another way of making nabla and G coupled. It's coupled in a way that the quasi difference is equal the torsion of one connection, which effectively is equivalent of saying that torsion of the conjugate connection is 0, right? And this is in fact with what is coined as what is known or referred to as the statistical manifold admitting torsion. So in other words, when nabla and G are torsion coupled, then this becomes a statistical manifold admitting torsion, or SMAT. Okay. So the term SMAT is coined by Korose, Matsuo, and Hemi again. So now the two notions, quasi-couple and torsion couple, they become one and the same if both torsion of the connections are 0. So then they are the same. Quasi-couple is torsion couple. They make a difference when the connections are allowed to carry torsion. Okay. So now with that, because of the curvature relationship, if we take one of the connection curvature free, then the curvature of the other connection has to be also 0. Now torsion depends on what assumption we make about the torsion. We can take quasi-coupling, which make the torsion of nabla and nabla star equal, or we can take torsion coupling, which make one of the torsion of one of connection to be equal. So because of this choice, we can look at basically the two models, the A model and B model. So the A model, we take the nabla and nabla star to be both torsion free, okay, the standard model. In B model, we take nabla, one of these, let's say nabla star, to be flat, and in doing so, essentially we are treating the parameter as having an affine coordinate chart, having affine, at least locally, an affine coordinate chart. So for the standard A model, the metric is Fisher-Rao, and so is in the B model. And for G and nabla, in standard model, they are quasi-coupled, and so is nabla star. They are both quasi-coupled with G. But in the B model, nabla and G are torsion coupled, and nabla and G and nabla star are not coupled, neither quasi nor torsion coupled. the curvatures of the nabla star in the standard model are not equal to 0 in general, but the curvatures of B model are both always equal to 0. Torsion of the nabla star are both 0 in the standard model, but in this case, in the B model, one of them is not equal to 0 and the other is 0 because it's torsion coupling. The manifold becomes Hessian if curvature of this vanish. The manifold becomes Hessian if torsion of this vanish. The A model is induced by the contrast function. B model are induced by so-called the pre-contrast function. And this is again due to the work of Matsuzoe and Hemi. And the manifold, this is called the statistical manifold. And in this case, B model, it is called a partially flat manifold. So let us now construct explicitly the B model, okay? So this, we need to introduce this notion of so-called a frame. So frame is a collection of locally linear independent vector fields, okay? So B1 through Bn are all vectors. So we have a collection of locally linearly independent vector fields. And so long as it's an orientable manifold, we would always have a frame. And now the frame becomes a coordinate frame if the Lie bracket of any of these frame vectors are equal, are 0, or vanish, the Lie bracket vanishes, okay? Now, given any frame, we can define a so-called bi-orthogonal frame. A bi-orthogonal frame is another frame that is in another set of linearly independent vectors, such that if I take in one vector from one frame B and taking another vector from another frame, the B star, then taking the two vectors G outputs a number, and that number is delta ij. It's bi-orthogonality. So that is a notion of bi-orthogonal frame. It is a generalization of so-called bi-orthogonal coordinates. In the Hessian manifold, we have the bi-orthogonal coordinates. In general, we don't have bi-orthogonal coordinates, but in general, we can always have bi-orthogonal frame. And in the case of the frame, so this frame may not be a coordinate frame. So in other words, this, you cannot write them as the partial derivatives of the bases, cannot be written as the coordinate base. Given any frame, we can associate an adapted connection to it. In other words, we can construct a connection as will be shown in the next slide. And this connection has a property that the curvature is always 0, and the torsion in general is not 0. Torsion of this associated connection or adapted connection in general is not 0, and it precisely equals the Lie bracket of the vectors in the frame. And when this frame is a coordinate frame, that is, when the Lie bracket vanishes, then this connection is also torsion-free. And torsion-free and curvature-free becomes a flat connection. Okay? So now let us construct explicitly this geometry, this connection. So given that the vector a frame, any frame, we can denote the B's, as we use this B matrix to denote this entire frame using the B matrix, and we can explicitly calculate. We can give this particular connection, which is using the B matrix. This is the inverse of the B matrix. This is a derivative with respect to the base, the coordinates that we have. So we in the paper that appeared in Information Geometry Journal, we show that what we showed is that now, given any frame B, we can construct an adapted connection, nabla B, and we can construct its bi-orthogonal frame B star. From the bi-orthogonal frame B star, we can construct another connection, nabla B star, right? Okay, so starting from a frame, we construct a nabla B from the connection from that, and we construct the orthogonal frame uniquely. And the orthogonal frame also supports an adapted connection, nabla B star, and we show that these two operations are commutative in the sense that the pair of adapted connections constructed from the pair of bi-orthogonal frames are conjugate connections. In general, they are curvature-free, but they may carry torsion. Okay, they are curvature-free, they may carry torsion. So bi-orthogonal frames are generalizations of bi-orthogonal coordinates for dually flat space. So in those cases, we always can have, for any probability models, we always have this bi-orthogonal frame. Once we have the bi-orthogonal frame, we can construct what is the bi-orthogonal frame. So if we have a parametric statistical model, right, we use the x parameter to represent the Fn parameter for a flat connection. So we look at the bi-orthogonal frame with respect to the x coordinate frame. This bi-orthogonal frame is nothing but the natural gradient fields, not just one gradient direction, but natural gradient fields, okay, the natural gradient fields. So we have the proposition that for any parametric family of the statistical models, we use the Fisher-Rao metric as the Riemannian metric, and then we can use x as the flat coordinates for one of the connection. Then the other connection, the other conjugate connection, is always a bi-orthogonal frame, and the G is a natural gradient, and that always is a connection that is curvature free but may contain torsion. Okay. So with this way, we can now study this natural gradient flow. So the natural gradient flow in this viewpoint is nothing but the bi-orthogonal frame that's associated with the flat connection. So it turns out that because the geodesic equation is symmetric in terms of the lower indices of the Fn connection, so the connections which admit torsion will have the same geodesic flow with respect to after you symmetrize that. So in those, the torsion does not contribute, torsion does not alter the geodesic. So the geodesic in this case is very simple to write out because we use the x as our the coordinates for the flat connection. So it's very easy to write it out. And so we can write out so basically the geodesic equations, we can write it out for the conjugate, for the other connection. For one connection, because it's the flat, the Fn coordinates, so these are just straight lines. So the other sets of geodesic is just simply like you can write it in this way. And so partially flat geometry is a special case of the SMAT. And then so now in a recent work, Hemi and Matsuzui propose a so-called a canonical pre-contrast function. They write it in some integral form, and then we explicitly calculate that in our model. And after calculation, we find out that the canonical canonical pre-contrast function takes a very simple form, which is the x coordinates minus x prime. So these are 2 points, x and x prime are the 2 points, and you use the Gij. So the difference, it's a very, very simple and trackable form. Okay. So this is also in the paper that we published. Okay. Now, when the coordinate frames are when the bi-orthogonal frame are coordinate frame, when the G bi-orthogonal frame is a coordinate frame, then it turns out that this flow field, so the frame is essentially just the dual coordinates with respect to x. So U are the dual coordinates, and B matrix are the Jacobian matrix. So you recover the standard bi-orthogonal coordinates, which is the case of the Hessian geometry. So things all work out nicely as we anticipated. So we gave the example of, say, a normal distribution. So in the normal distribution, we know that we do have it's an exponential family. So you have the natural coordinates and expectation coordinates, and there are dual potentials associated with that. We know. So that's the A model of the exponential family. Now, B model of the exponential family works like this. So we still have the Fisher-Rao metric, but now we write it down in its statistical parameter, the mu and sigma, we call it statistical parameter. And these statistical parameters, G written down, it has this very simple form, yet it cannot be written as the second derivative of some function. Okay, it's not the Hessian metric in this case. So the B model turns out that the two coordinates, the Lie bracket does not vanish because it has this precisely gives rise to the torsion, and the coordinate bases are as follows, like this. Okay. So I think my time is up. I just want to generally mention that the torsion carrying connections has some interesting properties that we just recently worked out. That was recently worked out in a publication with another collaborator, in which if we enhance the statistical manifold with almost complex structure or almost paracomplex structure, then torsion and this almost complex structure or almost paracomplex structure interact in a very interesting way to lead to both the complex structure being almost complex structure being integrable becomes a complex structure, and also the nabla being the holomorphic connection on this. So we have that, and then worked out, and then we also worked out some theorems about how this Kudazi coupling with respect to actually 4 connections that can carry torsion. So this program of looking at affine connection that carries torsion is something that is of very active research or active interest. And then we have some other Kähler structure as well that works out with the affine structure. So let me just conclude by saying that. So we're working on a new theory again together with Gabriel Kang on this B model. Turns out B model supports a very nice called the mirror symmetry. We will have a paper coming out that basically claims that in statistical model there is a kind of a mirror symmetry. The mirror symmetry resembles the kind of mirror symmetry that people see in string theory. So statistical mirror symmetry actually relates to the so-called reference representational biduality, and then we basically will ask the question whether there is a string theory of statistics, and I think thank you very much for your attention.